polynomials is equivalent to explicit solutions.
Okay, thank you for the introduction. It's a pleasure for me to speak here. So thank you for the opportunity. I enjoyed my stay here in Korea. And today we talk about the polynomial method. That's not my newest talk, but it's my most general one. So I hope everybody of you can take something home that you can use later. It's really very flexible in application. So I want to start with something that everybody knows. So that's this fact here. A polynomial of degree n has at most n roots. Here it's slightly different, of degree less than d1, has less than d1 zeros, except if it's the zero polynomial. And then I found a reformulation of this. That's the second thing here. Polynomials of degree less than d1 have on d plus 1 given points. So we fix d plus 1 given points. Let's say like this here. That's d plus 1, 1, 2, 3. And then we look only at the polynomial function restricted to this set. So on this set here of points, there's not exactly one non-zero. This means the polynomial function doesn't look like this here. Not one single peak. Yeah. So now this looks a little bit like double negation or so. Maybe we can prove it at first. So assume we would have exactly one trivial solution, trivial non-zero, then we have n other points where it is 0. So, or d1 points where it is 0. And then according to this first sentence here, it must be the 0 polynomial. Okay? So, but the 0 polynomial does not have a peak. So that's a contradiction to the assumption that we have one peak here. So this formulation has now an advantage. Some people say that one advantage is that you don't have to exclude this case, but the main advantage is that you can generalize it to polynomials in several variables. So now we don't look at just d1 points, we look at a Cartesian product. Let's say that's here a 3 times 3 grid, but I call this a 2, 2 grid. So it's always plus 1 here for some reason. And that's just two-dimensional. Here we have n variables. And then we look at the polynomial function over this grid here. And it does not have one single peak. So I will state this more clearly, more precisely in 1 minute. If you have questions to this, just wait 1 minute. Okay? And the first part of my talk, the first half, is about this not exactly one theorem. I call it a not exactly one theorem. And it has very nice applications. Somehow you can prove that many problems do not have exactly one solution. And then on the other hand, many problems have exactly one trivial solution. If you put this together, then you know they have a non-trivial solution. So let me make this more precise. So we have such a tuple of natural numbers, and I work here over an integral domain. An integral domain is always contained in a field, but for some reason I wrote here integral domain. And then a D grid, for example here, a 2, 2 grid is just such a Cartesian product of subsets here of the ring of this size, d1 plus 1, so 2 plus 1 is 3, and 2 plus 1 is 3 here. And always in this talk, whenever you see such a X here, then it's a D grid. And whenever you see a D, then there is some D grid in the background. So these two letters are always related. And there are some special grids. This is the most important one, just 0 and 1. That's the Boolean grid. And sometimes if the ring is finite, you may have the full ring here in each xi. That's the full grid. And now, how does this not exactly one theorem look like? You see, that's a corollary here, because in the second part of my talk, I will present something stronger. And in the one-dimensional case, you notice a stronger fact. Maybe you never thought about it from this side. So there's something that's stronger than the sentence, a polynomial of degree n has more than n, has at most n roots. You can guess. We'll come to it later. Okay? And here we have this formula. If the degree is smaller than d1 plus d2 plus dn, then the set of non-zeros here, all points in the grid where the polynomial doesn't vanish, that's not exactly 1. And then we need also a corollary. In this corollary we have m polynomials, and here the ring must be a finite field. That's a serious restriction. And then again, the degree of the polynomials are small in some sense. And then we look at the simultaneous zeros of these polynomials. And there is not exactly one simultaneous zero. Okay? If you take here the full grid, always the full finite field, then that's the Chevalier-Warning theorem. But actually in applications, the Boolean grid is more important. And you can deduce this here from there. That's very simple. Just define this polynomial here. And then if the pi's here have a simultaneous zero, then the original, then this polynomial has a non-zero, if and only if. That's easy to see. So assume pi is 0, then this power is 0. So 1 minus 0 is 1. And if this holds for all pi, then you have just a product over 1s. But if one pi is non-zero, then you get here the q minus 1 power. That's 1. 1 minus 1 is 0. So we translate here non-zeros to zeros. I come back to this later. But one big problem here is that you always have to use a finite field. So when finite fields have characteristic, which is a prime number, so later you will feel the desire for a field of characteristic m, for any number m. That's somehow an open problem. I managed to make a theorem like this that looks like as if there would be a field of prime power characteristic. And in the case where these polynomials all have degree 1, that's Olsen's theorem. And in this case where they all have degree 1 and are homogeneous and so on, it's conjectured that it holds. But you need degree 1 for, it's conjectured for arbitrary numbers m. So in some sense, a theorem that looks like this, but that would look like as if there would be a field of characteristic m. I wrote something in the appendix. That's Arlon, Carly, and Friedland's conjecture. Okay. And now I leave the slide for some minutes. You have time. Go through it. It's important that you understand this. And then I make some asides, some not so important things. Maybe that's interesting more for the experts. So let me make this aside. So when I want to prove this here, in some sense for prime power characteristic, you need here a generalization. And here we look at polynomials over integral domains, but actually you need a little bit less. You need only that if you have this grid and you take the differences here in each of these directions parallel to the coordinate axis, these numbers must be non-zero dividers. That's one thing. And then I examined this case here. The ring is Z modulo mz, and m is not prime. And then it's difficult to say something, so I restricted myself at first to the full grid, r to the power of n. Okay? And then I tried to prove something like this, and there were two surprises. The first one, this theorem holds, with one very small exception only. That's the case n, m, the number of variables, and here the size of this ring is not 1, 4. So if it's in the two-dimensional case, the theorem holds, and in the if the ring is bigger than 4, it holds. And then, but the second thing was more surprising. Here you have this degree condition. Degree of the polynomial must be small here. So that's d1 plus dn. But over this ring here, you don't need this. So that's somehow a nice theorem now, because it's about all polynomials. And it says if you have such a grid, then the polynomial function over such a grid doesn't look like this one peak. Okay, that's just one thing here. I don't have an application for it, but somehow it looks nice. And of course, it's difficult to make the step from here to here. That's a trick here that works only over finite fields. And you can generalize it a little bit, but here it's different and over these rings. And I had some more remarks, I think, here. No. That's my asides here. And so if you have questions now it's a good time to ask. They are pretty simple, these theorems. So I come to the main example, and yeah, that's a good example, I think. Here. So we look at 4 regular graphs. So I will show you an example. And then we have to add one edge. So I call this edge here E0. And then this graph contains a 3 regular subgraph. In the proof that I will show you, I call this an extended 4 regular graph. We have one additional edge, and this edge set, the extended edge set, is E bar. But let me illustrate this small theorem. So that's a 4 regular multigraph. Multi stands for multiple edges. It may have double edges. And there is no 3 regular subgraph here. That's 4 regular, 1, 2, 3, 4 edges at each vertex. But we can extend it, and now there is a 3 regular subgraph. Okay, that's the next example. I tried to find a nice looking one. So you have degree 4 everywhere, and then you can search for a while, and you find that's a 3 regular subgraph here. Okay. Then I made another example here. Yep, I draw some lines, and yeah, if 2 lines cross here, when I put here a vertex, it has degree 4. But I didn't put a vertex at any crossing here, and there are some points where I didn't. I think it's 127 vertices. Okay, now you can try to find. And I tried before I made the next slide. Yeah, I'm sure there is one. And I'll show you why I'm so sure. Okay, that's the proof now. So a subgraph, we may identify it with its set of edges. If there are isolated vertices, we just throw them away. And each such subset here corresponds to such a tuple or vector of 0s and 1s. So we take the Boolean grid here. In the Boolean grid, the elements are just tuples in 0 and 1. So I make this part a little bit slowly. Okay, so let me make an example here. We take this graph here. That's 4 regular plus 1 edge. And then we have here edge E1, E4, E2, E5, E3, E6, and that's the additional edge. Okay, and then we work over the ring R equals F3. So, and we want to apply this generalized Chevalier-Warning theorem. So 3 is this number Q. And now we introduce some polynomials. Here it's in the general case. Let me see. It's a very simple polynomial. Just a sum over those variables which belong to an edge that is incident with V. For each vertex V, we have a polynomial. So if I take here the vertex V1, then we have one polynomial corresponding to this. And that's just the sum over the, we introduce one variable for each edge. So here we have E1, E2, E4, and E5. So it's x E1 plus x E2 plus x E4 plus x E5. And then we can do the same with a vertex V2 and so on. And here we only have 3. Okay. So let's say that's V2 and V3. And what about the simultaneous zeros of this polynomial here? I say the simultaneous zeros here are 3 regular subgraphs. If you take this correspondence, so let me explain the correspondence. So if you take here a subset like this, and let's say this edge, that's 3 out of 7 edges, so we have here 7 tuples, and at E1 we take a 1 for this edge, E2 is not marked, and we have E0 here, so we have a 0 before that, 1, 2, 3, we have E3, we have E4, and we don't have E5 and E6. So this 3 edges correspond to these 3 ones here. Okay. And so now I'd say the simultaneous zeros are the 3 regular subgraphs. So why is this? Assume we have a 0 here for one vertex V. Then this means the sum is 0 modulo 3. So it's either each summand is 0, or 3 are 1, or 6, but we don't have 6 because the maximal degree is 5. It was 4 regular plus 1 edge. Okay, so for each such equation we get either a vertex of degree 3 like here, or a vertex of degree 0. That's an isolated vertex and we throw it away. So just let me tell you now why we have such a simultaneous 0. We check the degree, that's straightforward. You count edges and so on. You need double counting, I guess. And that's the elegant way to prove now that there is a non-trivial solution. By our generalized Chevalier-Warning theorem, we have not exactly one solution. But on the other hand, we have one trivial solution. The empty subgraph is a 3 regular subgraph. And if you put this together, then you have it. That's at least one non-trivial solution. Okay? That's the proof of this theorem. Are there questions to this one? I think that's a good example. If you later in your life want to apply something like this generalized Chevalier-Warning theorem, maybe this helps you. Okay? Where you need the additional edge, you mean? That's a good question. You need it here, you see, from E to E bar. So if you look at the degree of this polynomials, the degree is actually too big. So you, so you might make the grid a little bit bigger, and then you have this degree condition. It must be smaller than it's a Bayesian grid. So D is 1, 1, 1. That's 7 in this example here, and the degree in this example is 1, 1, 1. So you have 2 times 3, it's 6. 6 is smaller than 7. Okay? That's where you need it. But I can also mention you don't need the additional edge if the graph is not a multigraph. I don't explain this today, but then you don't need the additional edge. But it's based on this proof.
That's why your figure, the curve that you made the graph, you know that.
Yeah, I didn't, yeah.
It's not a multigraph.
Yeah, I think that was not a multigraph. Otherwise, you need the additional edge. You're right. Yeah, so you see.
Okay, maybe it is a multigraph, but you can make it to not be a multigraph.
I think maybe it's not. Maybe I looked at it once. I show you one other example, and I think it should be a 1 hour talk or 50 minutes or.
50 or 1 hour.
Okay. Okay. So I make one more example, a very simple one. It also has applications in additive number theory. For example, there is the Erdős-Ginzburg-Sif theorem, and I make something simpler. So let me take 7 numbers. 4 plus 4 plus 4 plus 5, 5 plus 6 plus 6. That's 7 numbers. And I want somehow that they sum up to 0 modulo 7. And in order to make this happen, we can erase some of the summons. And actually, it's not too hard in the small example here. That's 5 plus 5 plus 4. That's 14. It's congruent 0 modulo 7. But you can prove it for any prime here. If you take p many summons. And the way to prove it, it's very simple. I mean, erasing somehow just means to multiply it with 0. And let it in just means to multiply it with 1. So if we don't know what we want to do, we put here a variable. So here we put x1, x2, x3. And again, we take these variables out of 0 and 1. And then we check that this polynomial has low degree. So it has not exactly one solution, but it has the trivial solution. You could erase all. Okay, that's another thing, how you can work with this. So now I explain this here again, but in a more abstract way. So maybe you can learn from this as well. So actually one can prove any problem that has a non-trivial solution can be proven in such a way, somehow. I call this polynomial here an algebraic solution. Basically, the job is done once we have it. Just have to have low degree. So here is the piece of chalk. So I make this definition. If I say you can prove any problem, solve any problem in this way, what's a problem? So problem, and that's is a pair. Yes. S as trivial of sets with S contains S trivial. So, and the main question is then, is S equal to S trivial? Okay, so in this example, we take as trivial solution the trivial 3 regular subgraph, the empty graph, and as solutions just the set of all 3 irregular subgraphs. So you can state any problem in this form. I mean, set is nothing very concrete. It's a very general definition. So how can we solve such questions? And one way is the following. And to make it more easy here.
Usually you want to prove S is not equal to S.
Yeah, but that's why we ask, is it equal or is it not equal? Okay? And to make it more easy here in the talk, I assume that S trivial has exactly one element. Then we have here the set S. Let's say that's S. Here that's S, and we have a subset that's S trivial. So that's in this case it's just 1 point. And how did this proof work now? Well, actually we found an even bigger set in this proof here, and in this proof this was somehow the set of all subgraphs, or the grid. The set of all subgraphs, yeah, let's say the set of all subgraphs at first, and then we take the grid. So in this case it was a Boolean grid. Here I make something bigger, just 2-dimensional, and somehow you have to bed it in. Okay, so you get your set S here, and then you have 1 point which was the trivial solution. Okay, so somehow you have to bed it in into such a grid, and on this grid that's over some ring, and we can define polynomials there. And now one can prove if there is a non-trivial, one can prove and can always define a polynomial that is 0 here outside of S and non-zero. It's hard to draw here. I mean, it's inside S it's non-zero. Yeah, it's like a hill here, but outside S is 0. And if there is a non-trivial solution here, then you can achieve this low degree here. So in some sense there is such a polynomial. I mean, here in the background, here we worked with simultaneous zeros, but if you remember back, it was 1 polynomial and a non-zero of this. So here we have such a polynomial that is non-zero on S, and it has small degree if there is a non-trivial solution. And then you can apply this theory here behind this and can prove it in this way. Yeah, but now it's the question, did we really understand this? And why should it be easier like this? I mean, here in this case it worked. But why did it work? And you have to look closer. I mean, here we don't talk about one graph here. We have talked about infinitely many graphs. So we don't talk about one problem, we talk about infinitely many. And now if you have such a problem, and you try to solve it and draw a graph and mark a 3 regular subgraph, you have a lot of work. So I call this the finite blackboard problem. You run out of space, end of time, and so on. But what we managed here, we found a solution for all these infinitely many problems at the same time. So this polynomial here, or this set of polynomials here, they fit into one general form. This, you can write this down here, and it holds for all 4 regular graphs plus 1 edge. Okay. That's, I think that's a main point. For some reason, sometimes it works, and you find such an algebraic solution that And everything fits into one form, and then it's a nice proof, usually. There are many nice proofs using this. Okay, so now I come to the second part of my talk. So are there any questions left to this here? Or yeah. That's a good question. You can apply this to higher regular graphs, but for example, if you want to prove that a 10 regular graph has a 6 regular subgraph, then 6 is not a prime power. And I told you we don't have such a theorem for simultaneous zeros for non-prime powers. So I think for 6, 10 and 6 here nobody knows if this holds. But for prime powers you can prove it if this number here is a prime power. And then I think this number minus 1 times 2 is this number also. Yeah, so there is some theory. And in particular to this theorem, there's I think at least one paper where they examine this without the additional edge for simple graphs. Okay. Okay. Now I told you there is something behind this, not exactly one theorem, something more.
Number 4 is not coming into play in this.
It comes into play, you add one edge, then the degree of each vertex is at most 5. And you need it here for the sum. It should never be 6 somehow, because, yeah. So it comes into play. And yeah, of course, somehow in this degree calculation, it's also somewhere here. Okay. Then I show you this formula. Okay. That's a sharpening of, was it the right direction? Okay, we switch to this. So we have a grid, a digrid, and we have one polynomial, and the coefficients here of that's multi-index notation to this monomial, that's p delta, and the total degree is restricted, but here now we have not smaller, we have less equal. Okay, and then there is one coefficient inside this polynomial here. That's when you take the size of the grid and take the coefficient with a d here. Not this formula holds only for 1 usually, and then you can express this coefficient as a function of the function values. So it depends linearly on these function values, and the coefficients are complicated. And they are actually not in the ring usually. So you have to be careful with this as well. So if you are over an integral domain, then they are in the quotient field. Okay. And I mean, there may be some other coefficients for which you have a formula like this. For example, if you have a 0 in your grid, then you know P0, that's the constant term. It's a function of it depends only on the function values. It's a very simple formula, but for general grids, that's the only formula. And then we have two corollaries. The first one is if the coefficient is non-zero, then the polynomial map here cannot be 0. Okay? There must be at least one summand which is different from 0. So there's at least in the end one point where it is non-zero. That's the combinatorial Nullstellensatz. And the other corollary is if you take here 0, so for example, if the degree is strictly smaller, then this is 0. It belongs to a monomial of maximal degree, and then there cannot be exactly one summand which is different from 0. So you get this theorem here. There's not exactly one theorem as a corollary. Okay. And I want to show you the proof as well. And there is something stronger. I mean, if you have stronger conditions, that's the... I know that was our Chevalier warning as the next corollary. but somehow there is this interpolation formula. You have again a Discrete, and now you start with any map, and you can interpolate it with a polynomial with restricted partial degrees. So restricting the partial degrees here is much stronger than restricting the total degree. But if you do it, then you get a unique interpolation polynomial. So there is a polynomial that interpolates this map Y here. So on the grid, they are the same. Okay? And you have a formula for the coefficients. It's interpolation formula. You usually learn about interpolation algorithms. Because it's complicated here, you have fundamental determinants and then tensor products of matrices, and it's complicated. But in our theorem, we dropped here this condition, and we took the total degree is smaller than the sum. And under this weaker condition, this formula gets lost. But it doesn't get lost completely. There is one coefficient for which it still holds. That's for D here, in the place of delta. And in order to prove this, I made here this corollary. So now we start with a polynomial, not with a map Y. And then, of course, the polynomial describes a map, so like here. And you just plug in this map here for Y. Then you can express the coefficients of the polynomial as a function in terms of its polynomial map. Okay, now how to prove the coefficient formula? So at first we somehow modify our polynomial that has restricted total degree. And then we get something that I call a trimmed polynomial, P mod x here. And it describes the same polynomial map. It has the same leading coefficient, how I call it. And this trimmed polynomial has restricted partial degrees. So to this trimmed polynomial, we can apply this interpolation formula or this corollary, and then we have the leading coefficient here of P is the same as the leading coefficient here. And then this has restricted partial degrees, so we apply this interpolation here. That's this formula. And then by 1, we can replace this polynomial map here by this. And then I introduce some other names here for this coefficient. Okay. Then we have this formula. But how to modify P in such a way? So the polynomial P has restricted total degree. That's this slanted line here. It's somehow a simplex. The coefficients lie only somehow close to this. Yeah? And now we modify this one by adding some other polynomials. So here I added basically this product here. And that's something that is 0 on the grid. And then we shifted it here 2 upwards. That's why this box here starts only here. And we multiply it now with a suitable coefficient in such a way that in the sum, this coefficient cancels. So then we have eliminated this one. Now we eliminate this one. And so on and so on. And you see, whenever I eliminate something, we add the polynomial, so the coefficients here change. All the coefficients change. But there never was a box lying over this coefficient. So it's still the same. It's unchanged. Yeah? So that's how to prove this theorem. Okay. And before I come to the applications of this formula, somehow this game becomes easier if you have only ones and zeros here. And there are many problems where you can get this somehow. All these flow conjectures or coloring problems and for color problem. And you can apply some tricks in order to get here a cube instead of such a simplex. And then adding such a box is just Berlekamp switching game. So you have ones and zeros. You may imagine them as lights which are switched on and off. And you can switch whole rows and columns. And then in the end you can prove that, for example, the four-color problem, if you take a map, then you can translate the map into such a pattern here. And if you can switch it off with this Berlekamp moves, then that's a counterexample to the four-color problem. So there are many problems which can be studied in terms of this Berlekamp switching game. Okay, that's one remark. Now we go on with this formula. That's the first line here, and it looks a little bit full, but that's the last slide. Okay, so that's the general case here, an arbitrary polynomial of low degree. And now we plug in something special. We start with a matrix, and I call this here the matrix polynomial, or the generalized matrix polynomial. We could put here 0. So x is a tuple like x1 to xn, and if you multiply it with this matrix, you get a vector with entries x in x, polynomials in x, and you just take the product over all these linear polynomials. And if you plug this in here, then somehow this coefficient PD depends only on the matrix A here. Yeah. And it's in some sense something like a permanent. I gave a definition in the appendix. That's something similar to the determinant. Okay? And if you take now a 1-1-1 grid, so that's each x has 2 elements, each component, then this becomes simpler. Yeah, you can take the Boolean grid, for example, then that's a formula for the permanent. That's Reiser's permanent formula. If you put here 0 and take the Boolean grid, then 1-1-1 is the usual permanent. And now you can take special matrices. You can start with a graph. Here we take a graph, and we want to study list coloring. So we have at each vertex a list of colors. Let's say to the vertex v we have xv. And the list coloring is just, in the end, a tuple here in this product. You take for the vertex v an element in this set xv, and for another vertex w, an element in xw, and then you get such a tuple. And but we also can make here the incidence matrix of this directed graph. And this incidence matrix looks rather simple in some sense. I mean, in each row or column there are only 1, 1 and 1, 0. So this becomes more simple. We plug in here 0, and we get the differences, the sum over all differences, where S and T are vertices that are connected. There is an arc from S to T. And so if this product here is non-zero, then all the differences are non-zero. So it's a correct coloring. Okay? So we have this formula where somehow in this only correct colorings count here. Otherwise you get a 0. And you have this permanent here. And you can look a little bit at the definition and so, and you find out in the end it has something to do with the Eulerian subgraphs, and those with even many edges and those with odd many edges. So if they are not the same, then the left side here is non-zero. This means there is at least one summand which is non-zero. So it means there is a list coloring. Okay? That's Alon and Tarsi's theorem, which has many applications, and it's particularly simple if you take a bipartite graph here, like this. In this case, this E-even, the Eulerian subgraphs with even many edges, contain the trivial graph, and E-odd is the empty set. I mean, any circle has even length. So you have here one element and here 0, so the difference is different from 0. So this works particularly nice with bipartite graphs. Okay, but we can make it even more special here. Yeah, we take now the line graph of a planar k-regular graph. So for example, if you study the 4-color problem, you can study planar 3 regular graphs. And in this case, it turns out that the coefficients here are pretty simple. They are all the same. You need planarity to prove this. But then you can prove they are all the same. And so basically, also these products here are all the same. If they are non-zero, you get here the number of colorings of this line graph, and the vertex coloring of the line graph is the edge coloring of this graph. And in the planar 3 regular case, the edge colorings correspond to the face colorings, for example. So that's Schaim's formula for the number of colorings of a planar 3 regular map. And that's a very special case now from this. And yeah, there are some other remarks. I still have some minutes, I guess. So let me talk about some other remarks. Yeah, for example, in this planar 3 regular case, there we know by the 4-color theorem, this sum here, there are colorings. So the sum here is non-zero. But now the left side of this equation here, or here, it doesn't depend on the grid. Okay? So we can change the grid now, and the sum doesn't change. But changing the grid here means just to change the color lists. So then we know we've changed color lists. It's still different from 0, so there's a non-zero summand, so there's still a coloring. That's how you can prove the list coloring conjecture for planar k-regular graphs, or 3 regular graphs at least. So it's conjectured that the list chromatic index of any graph is the same as the chromatic index. So if you have a normal coloring, you get also list colorings, if the lists have size 3. Okay? Yeah, I guess that's basically everything. Maybe you find some new application, I hope so. And yeah, are there questions to this? No? Okay.
I used to be my job to ask questions.